I will now discuss the solution of a problem from the section Real Analysis. And the problem is based on the properties of continuous functions. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022, and it is from the part C. The given question is, let A be a subset of R, where R is the set of all real numbers, and F be a map from R to R, and it is given F is continuous. Which of the following statements are true? Which of the following statements are true? Options. Option 1. If A is closed, then f of A is closed. Option 2. If A is bounded, then f inverse of A is bounded. Option 3. If A is closed and bounded, then f of A is closed and bounded. Option 4. If A is bounded, then f of A is bounded. We have a subset A of the set of real numbers. We have a function f from R to R, and it is given f is continuous. Then we have to discuss which of the following four statements are true. There can be more than one answer. So spot out all those appropriate correct answers from the given four options. Now, before entering into the discussion of the solution of the given problem, we remember a very well-known theorem called Heine-Borel theorem. Let A be a subset of R power k, that is a k-dimensional Euclidean space. Then E is compact if and only if E is closed and bounded. Compact implies and implied by closed and bounded in R power k. Agreed. This is a very well-known theorem. What will be the continuous image of a compact set? And the theorem says it's again compact. Continuous image of a compact set is compact. So these two results we will be using in finding out the correct statements from the given four statements. So we have this. Now let us take down the option 3. The statement given in option 3 we have written here. If A is closed and bounded, then f of A is closed and bounded. We will discuss the validity of this statement. Yeah, we will establish this. Now suppose that A is closed and bounded. So it's a closed and bounded subset of R. So if it is closed and bounded in R, use Heine-Borel theorem. So by Heine-Borel theorem, A is compact, because in R power k, E is compact if and only if E is closed and bounded. So by Heine-Borel theorem, A is compact. Because f is a function from R to R and it is continuous, so f of A is compact. This because it is a continuous image of a compact set is compact. So f of A is compact subset of R, because continuous image of a compact set is compact. So this implies f of A is compact subset of R. Means again use Heine-Borel theorem in the reverse direction. Then f of A is closed and bounded subset of R. So f of A is a closed and bounded subset of R. So by Heine-Borel theorem. Thus, A is closed and bounded subset of R implies f of A is also a closed and bounded subset of R. So thus, we have proved the statement given in the option 3. Thus, the option 3 is true. we continue and let us take down the statement given in option 4. It states, if A is bounded, then f of A is bounded. Yeah, for this also, we will establish this result and prove that it is true. Suppose that A is a bounded subset of R, correct? So this is our hypothesis. Therefore, if A is bounded, means A has its infimum and its supremum. Agreed. Let lowercase m, small m, is the infimum of A and the uppercase m, capital M, is the supremum of A. Agreed. So, therefore, yeah, small m is infimum of A, capital M is supremum of A, means m, small m, less than or equal to x, less than or equal to capital M for all x belongs to A, because small m is infimum, capital M is supremum. That means A is a subset of the closed and bounded subset m to m, small m to capital M. Note that it is the closed and bounded subset m comma m is compact because it is closed and bounded. Correct? You are using Heine-Borel theorem. So this implies, and F is a continuous map from R to R, and this is this is a closed and bounded subset m to m, and it is compact. So the continuous image f of the closed and bounded subset m to m is also compact because f is continuous and that is compact. Then the continuous image of a compact set is compact. Therefore, this is also compact. So, because it is compact and it is subset of R, so it is closed and bounded. Use the Heine-Borel theorem. So, f of the closed and bounded subset m comma m is a closed and bounded subset of R. But we know A is contained in the closed and bounded subset, closed and bounded interval small m to capital M. So A is contained in this. Therefore, A is contained in this. This will imply f of A is contained in f of this closed and bounded interval m to m. So f of A is contained in this, but f of m to m is what? Is closed and bounded. It's bounded. So f of A is also bounded. So f of m to m is closed and bounded. So f of A is contained in this, but this is bounded. Therefore, f of A is also bounded. Right. So that means what we have proved is, if A is bounded, then its image f of A is also bounded. Agreed. So thus we have established the truth of the statement given in option 4. So the option 4 is true. So far we have proved 2 statements given in 3 and 4 are true. Now let's move to the next option, option 1. If A is closed, then f of A is closed. For this, this is not true. To say so, we have to give a counter example. Yes, we give a counter example. The counter example is a very well known example. We take, let f is a map from R to R defined by f of x is equal to e power x exponential function, x belongs to R. It is very well known. Exponential functions are continuous functions. So it's a well known result that f is continuous on R. Agreed. Now let A is the whole of the domain, that is R. Then f of A will be, so f of x is e power x. Now A is the whole of R. F of A means the image of f, the image of A under f. And this will be positive, because e power x will never be 0, and it is positive. Therefore, it is the open interval 0 to infinity, positive real numbers. F of A is the set of all positive real numbers. Now, A is the whole of R is closed. Yes. A is capital R means what? It is minus infinity to plus infinity. It is both open and closed, so we take it is closed. But f of A is the open interval 0 to infinity and it is not closed. The reason being that 0 is a limit point of the open interval 0 to infinity, but 0 does not belong to the open interval 0 to infinity. Therefore, it doesn't contain all its limit points and hence it is not closed. So, A is equal to capital R, that is minus infinity plus infinity, is both open and closed, therefore it is closed, but its image is not closed. This shows the option 1 is not true. Agreed. So let's move to the next option, option 2. If A is bounded, then its inverse image, F inverse of A, is also bounded. Is it true? And not all, you see, we give a counter example again. So let f r to r be a continuous function defined by f of x is equal to c for all x belongs to r. That means we have taken a constant function where c is a constant. It's a constant. Every constant function is continuous. Yeah. So let A is equal to the set of all f of x, x belongs to R. That means A is what? A is f of x, x belongs to R. So all images we have taken. The images f of R is A. So where is A? A is in the codomain R. A is a subset of codomain. So A is the singleton C only, because f of x is C for all x belongs to R. Therefore, A is precisely consists of only one element, that is C. And you know it is a finite set in the codomain. Every finite set is bounded. So therefore, A is bounded. A is the singleton C is bounded. So what is its inverse image? F inverse of A. F inverse of A is the whole of, now F inverse of A is the whole of R. Is the whole of f of x is equal to C, x belongs to R. The inverse image of the set A, that is the singleton C, is the whole of R, that is minus infinity to plus infinity, which is unbounded. So A is bounded implies F inverse A is also bounded is not true. Therefore, the option 2 is not true. So far, what is that we have proved? So options 1 and 2, we have proved they are not true. Options 3 and 4, we have proved they are true. Therefore, our answer to this question is options 3 and 4, which are true. So that is the detailed discussion of the solution of the problem from the section real analysis, and the problem is based on the properties of continuous functions. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.